Alrighty, so has been a while, and so because there, as I said, so I have quite a lot to talk about. Sorry, by the way, that I completely completely forgot to submit the updated slides. So they are online now, so they're on Blackboard. So today's slides, but I did it literally like 2 minutes before the class started. So if you want to download them now, so they're there, but it was a little late this week. Okay, so it has been a while since we talked about regression, and so just a little bit of a reminder, right? So in simple linear regression, so we are estimating our linear regression model. That means we find so the line, the straight line of best fit, so that describes the relationship between our predictor variables, right? So the most commonly denoted by X, and our outcome variable, so most commonly denoted by the letter Y. And then there are different terms, right, for predictors. So they're called, so the X values are called predictors, independent variable. So what could it be? I have more more options for the Y value, but it's the outcome, the dependent variable, the criterion, the response variable, right? So there are more for the predictors as well. Sorry, I'm just so they don't come to mind right now. So right, these also, everybody has their preferences, how they are, what labels or what names they're using, but it's right, interchangeable. So all means the same thing. And so when estimating our regression model, we are basically estimating two regression parameters, which is our intercept. Yeah, so that is where our regression line meets the y-axis. And so then again, so that is the expected value of y when x equals 0. In most cases, so we can, in many cases, we cannot interpret that intercept in a meaningful way. And it depends on whether that our sample actually includes cases that have that particular value, right? So, and often it's just a mathematical, some theoretical value, so that has no further meaning for a regression model. And so it doesn't matter anyway, right? So I explained that so before spring break. So for example, whether the intercept is significant or not, we couldn't care less. It's just a constant, right? It's just basically it's a scaling parameter. If we would standardize our predictor and the outcome, then it would be 0 anyway. So it doesn't really matter. Okay. And so then the actually really important parameters are slope parameter, right? That's often I will refer to that as the regression coefficient, right? So although in so strictly speaking, there are two, right? So the intercept and the slope, but the slope is so the most important one. That's what we are interested in. We want the slope to be if we are hoping for to show that there's a relationship between the predictor and the outcome, so then we're hoping for a slope that is not 0. And so then again, so the slope so shows the direction of the relationship, right? So whether it's if like the slope is positive, you have a positive relationship. If it's negative, you have a negative relationship. And so it is, so the slope indicates what is a change in the outcome variable and our response variable as the predictor variable changes by 1 unit. So that of course depends on what the units for your predictor are. So right, so what is the change in the mean, I should say, of your outcome variable if your predictor changes by 1 unit? And then again, right, so for each value, so basically what we're really estimating when we are fitting this regression model is the mean. So it's the expected value of our outcome variable. So there will be, right, so if we have our predictor X, and so X could be something like so age, right? And then we're predicting height from it. So we will have multiple participants that have the same age. And then of course they will vary in terms of their heights, right? And so what the model is predicting is the expected value of height for that X values, for that age, right? And that is the basically the mean of this distribution, right? So the conditional distribution of outcome values for that given predictor value. Okay, so yeah, that was our example with the album sales. I just go over that again because at the end of class, hopefully I will be able to cover that. So we will get back to that. So the idea here was, whether it's meaningful or not, that so somebody wanted to find out whether so we can predict the so the number of album sales, so right, from the advertisement. So an advertisement was operationalized as a number of times a song was played on the radio in a given time period, let's say a week. And so and then so the scale, so the units for album sales was in thousands, right here. So the estimated model was so the intercept 88.97 and the slope 3.87. So that means the regression equation was the outcome y, right? So the album sales equals 88.97 plus 3.87 times x. And so that means, right, so each time a song from the album is played on the radio, the mean, right, sales number of albums increases by 3.87 units. And so that translates to 3,870 albums more sold, right, on average, again, because there will be many albums where, for example, so that are played a certain number of times on the radio, right? So as you can see right here, for basically if we're given like for 20 times, right? So we have multiple cases that in our sample for which so that is true. Okay, and then in this case, we don't, I mean, we are getting close to zero here actually. So in this case, it might even be possible, sort of, to interpret, although strictly speaking, zero is not really included in the data set. So, but here it might make some sense, right, to interpret the intercept. You could say that it's sort of some sort of baseline if you wouldn't advertise at all. If so if the album, songs from the album would not be played on the radio, so how many albums would be sold? But then again, so we will talk about that later. We cannot make predictions from values that were not included, so that are not in the range of our original predictor, right? So that are not in the range of our X variable on our sample, so that is not possible. All right, so that was just a reminder. And so let me actually move forward, right? So again, so to remind you of the key terms. So what our model is basically estimating is it's a predicted mean of our outcome variables given so the specific value of our predictor. And so that is these predicted means or predicted values are also labeled as the y heads, right? And so then of course, so for each predicted value, so we also have a number of observed values, at least one, right, and often several. And those observed values will deviate from the predicted values, right, in both directions, so either in positive or negative direction. And these deviations of the actual observed values, right, so for example, the album sales regression, so how many times the album was actually sold, right? So as opposed to what was predicted based on the number of how often a song has been played. So that is called the residual, also often called the error term, right? So this is this vertical distance. So the how much the actual y values or the actual outcome value deviates from what has been predicted based on our regression model, right? And so prediction is always on our straight line here. And when we are estimating our regression lines, so in standard regression, then we are doing it in such a way that the total residuals are minimal. Yeah, so that should be 0 on average. So the sum of our residuals, so the model parameters are estimated in a way that the sum of our residuals is 0 for our sample, and that the sum of the squared residuals is minimal, right? So these are the conditions for finding a solution for our parameters to estimate the slope and the intercept. And so that is also known as least squares regression. So, or the ordinary least squares regression. You will read that probably quite frequently when you look into other textbooks or the internet, right? It's OLS regression. So if you ever see that, the OLS, the ordinary least squares regression, and that is basically what we are talking about, right? So sort of our standard model. And we will talk about alternatives today because it comes with certain problems because despite its, right, so it's such an elegant and numerically easy, straightforward solution. It makes the parameter estimates extremely sensitive to outliers. And so that is a big disadvantage, and therefore so other methods that are more robust to such outlying models have been suggested. Okay, so as I said, so that was just a reminder of what we were talking about. And so, right, maybe one more, because so we will talk about that at the end of this class as well. Just a reminder, right? So I mentioned that several times. So when we were going over the previous slides, that so actually for each x value, we have a distribution of y values, so that share that same x value, and we call those distributions the conditional distributions, right? And so they are characterized, of course, by a mean. So the mean is just the estimated value, right? That's our y hat. And so the standard deviation of those distributions should be the same, right? That's one of the assumptions for regression models. So should be same across the entire range of x values. And so we just have to keep in mind, so that is the conditional distribution of y values given x, right? So that we're never talking about like one value, but always about several values, and they follow certain distributions. We make assumptions about the distribution of these values when we are trying to make generalizations to the population. We try to generalize our model to the underlying population, and it's important that these assumptions are met. So when we have no relationship between our predictor and the outcome variable, then our conditional distribution is just the basically the distribution of our outcome variable, right? So then it's just the same, because then in this case we would predict the mean of so our regression line would just be a horizontal line, and we would always predict the mean, in this case college GPA, right? So if we would use high school GPA to predict college GPA, right, and there was no relationship, then we would have a horizontal line, and so this horizontal line would be let's see, mean college GPA, and the conditional distribution of our college GPAs would be for each value of x, of course, the same as the as a population distribution. Right. So, okay. Good. So maybe let me actually just start with the assumptions, and then if there are like questions or things that aren't clear, so let's try to go back, because as I said, so there are quite a few things that we need to talk about today, and I want to make some progress, but so we can go back and repeat some basic concepts as needed. Okay, so of course, so as always, when we run our, when we estimate our regression model, right, when we do a simple linear regression analysis, or multiple regression, whatever, so we hope to be able to generalize the model that we estimated for our sample to the entire population, right? So that is our, in most cases, our hope, very few exceptions. And in order to be able to do so, we have to meet the assumptions of our inferential tests. And so, right, as you remember, if we wanted to test the regression model as a whole, we're using an F-test. So that is basically a test whether our R squared, so the variance in the outcome variable that is explained by our model, whether this R squared is significantly different from 0. So for our so regression coefficients, so especially for our slope parameter, right? So for our slope regression parameter, so we also test, so whether we can also test whether this parameter is or coefficient is significantly different from 0, and so we do that using a t-test, right? And so both methods are equivalent, so mathematically. Okay, so but again, so the assumptions for these inferential tests, so for the F-test and the t-test, so they must be met, right? And the t-test, as always, so we're dividing our sample statistics or coefficient by an estimate of a standard error, right? So the standard deviation of its sampling distribution. And so just going back, maybe for, right, so just this one slide here. So our F statistic was just this mean sum of squares. So for our model, so that means a variability in our outcome variable that is can be explained by the predictor, right? So that is basically the proportion of the variance in our, right? So for example, the college GPA scores that can be explained so by our high school GPA. And so that is basically how much the so that is the variability between our regression line and the mean of our distribution of the outcome variable. And and we are relating that to the residual or the error variance, and that is basically deviation of the individual observations from this estimated regression line, right? So how much they deviate, so how much residual variability we have. So that was the logic of the F-test, and so we have to meet these, so the assumptions that underline this test. Okay, and if so we are meeting those assumptions, then we have can be sure that a number of things are okay. And the first is that our standard errors are valid, right? Not inflated. They're not too small. So we are not underestimating them, and we're also not overestimating them. So that means we are not losing power by overestimating them, and we are not making so we're not inflating our type 1 error rate by underestimating them. So that also means so our confidence intervals are valid, right? Because they're directly based on the standard errors. And then finally our hypothesis test is valid, right? So which is also very important. And if these assumptions are violated, right? So we cannot generalize conclusions so from our regression model to our target population. We can still fit a regression model to our sample, right? In very much the same way as we can calculate a correlation coefficient for our sample. We can always do that, right? So nothing prevents us from doing that, and it's always valid to describe our sample. But what we cannot do is we cannot generalize that to the target population. And that is why we're doing statistics, right? In most cases, so that's not a good thing. And we also need to check for potential bias in our data. And that means we have to check for outliers. And in particular, so what we are most concerned about in regression is not so much outliers per se, but we are concerned about a nasty kind of outliers, and they are called influential cases. So we will talk about that in much detail. Okay. So there are assumptions in terms of so the variable type. So our outcome must be a continuous variable. And our predictors, whereas our predictors can be continuous or dichotomous, right? So both is possible. We can also have actually qualitative predictors. So there's something that's called dummy coding. We will talk about that in 2 weeks. Which is also unproblematic. So basically we can, so each design that you can analyze, for example, with an analysis of variance, so you can also use a regression model to analyze that. It's just the question of how you code your predictors. So you basically translate that into dichotomous predictors, a set of dichotomous predictors. And of course, for every inferential statistic, so for inferential statistics in general, for any statistical test, so we have to assume random sampling, right? So otherwise our results are invalid. So our predictors must have non-zero variance, so otherwise we cannot estimate, we cannot fit a model. And our, so it's always a must as well, so our error terms need to be independent. Yeah? So for any pair of observations, the error terms should be uncorrelated. We have talked about this idea of independent errors, independent observations. So basically another core set of assumptions that is more specific to regression and correlation is derives or can directly be derived from this request or requisition that says the data have to follow a bivariate normal distribution. And so the bivariate normality assumption encompasses 3 components. So that means that the first is linearity. It means that our residuals have a horizontal line relationship with the predicted values. So what does it mean? So that means that we do not basically, for example, our predictor value increases, then our residuals, the mean of our residuals should not increase as well, right? So that would be for our, so for example, for our high school GPA versus college GPA example. So if we had for higher or lower high school GPA, if we had basically a higher, basically so larger or smaller residuals so estimating the college GPA, so that would be a problem and that would violate this assumption, right? So again, we will demonstrate that later. So you can easily test that by just plotting the residuals against your predicted values, and then you shouldn't see anything but a horizontal line, right? So there shouldn't be any trend in the data. A second one is homoscedasticity. So that simply means that for each value of the predictor, the variance of your residual should be the same, right? So the spread of the residuals around that predicted value around your y hat should be constant, right, across the entire range of your x values. And so finally, your errors, your residuals should be normally distributed, right? So I use the term error and residual interchangeably. So basically, you can call it one way or the other, right? Residual error, same thing. So that means, again, for each value of the predictor, the error term should follow normal distribution, right? Should be normal distribution. The mean should be 0, and the standard deviation should be the same, right? So that is the these are the assumptions. Okay. So, and just to recap, yeah, so we need to run regression diagnostics. So to test the assumptions for statistical inference, so to make sure that we can generalize our regression model to so the target population. And we also have to make sure that the parameters of our regression model, so the model itself, is not distorted by outliers. right? Or in general, influential observations. And we have to make sure that the linear model actually provides an appropriate characterization of the relationship between our variables. Yeah? So we have talked about that before. If so often, so a poor model or large residuals, also a violation of the assumptions, can be explained by the fact that the model is simply not right. So if you have a nonlinear relationship between our predictor and our outcomes, and a linear model is not a good fit, right, and will result in huge residuals or so a violation of the homoscedasticity or the normal distribution of the error terms. So in many cases, we can fix that by changing our model or by also by data transformation, right? So some nonlinear transformation can occasionally help. So, but we have to spot the underlying problem first. So that means, right, our the parameters of our regression equation can be misleading. Yeah, so they can be so from looking at the parameters alone. So we cannot always tell whether they actually are a good description of the relationship between our variables. So whether they actually capture the most salient features of our data. And so there are two two major ways to validate the assumptions of our linear regression model. And the first one is residual plots. And the second one is to detect influential observations. And so that can be done either through plots as well, so visual displays, or numerically, right? So, and then again, so for most, we always have this, right? So either we check some assumptions with plots, and then we ideally supplement that with some numerical methods or statistical tests as well. Okay. So when it comes to plots, then because most of the assumptions in linear regression are centered on the residuals, right? So that they have the same standard deviation, so that they're that they're independent of each other, that they're normally distributed. So in most cases, what we wanted to plot are the residuals, right? And that is summarized under this umbrella term residual plots. And so these plots can be used to check many things. So we can see indications that the basically the linearity assumption has been violated. So that's actually the regression function, the relationship between the two variables is not linear. So we can spot heteroscedasticity using the residual plot. We can sometimes determine whether the errors are dependent, which is not good. And we can also tell whether the errors are not normally distributed. And we can also get an idea whether there might be outliers in our data. So actually we can tell quite a lot from our residual plots, which, as I said, so in most cases we are plotting the residuals against the either standardized or unstandardized residuals against the fitted values, so our y-hat values. And then we examine the patterns. So we will have examples in a second. Okay, so just as a reminder, right? So the residual is a difference between a case or observations or subject's actual value on the outcome variable and the predicted value y hat. So the value that is predicted from the linear regression model. And I mentioned that before, right? So the residual, so in most cases, when we're talking about residual plots, then we mean plotting the standardized residuals along the vertical axis and the standardized predicted values, so the y-hats on the horizontal axis. But there are variations, right? So that is the most common way to plot so the data. And in general, right, so what we want to see in those plots is that the residuals are randomly and symmetrically distributed around 0 for all values of y hat. So we want to basically see something that looks like a rectangular envelope, right? So we don't want to see something that looks like a funnel. So that is not a good thing, right? So anything that deviates from this rectangular shape is usually problematic. Okay, And this is just an example data set to illustrate how estimating a model alone can be misleading in many cases. So, and it illustrates actually the critical necessity of visual displays to assess your model and to assess how well it characterizes your data. So here you can see that these are artificial data. So, but they are here divided into 4 panels. So that's basically, so panel 1, it's always an X and paired observations, right? Always an so X variable and Y variable here. And so the data are manufactured in a way that the statistics are identical for them. Yeah, so you have these XY pairs and they have all identical means. I mean, not necessarily X and Y, but so for each pair, so all the axes have the same mean, the same standard deviation. So X and Y always have the same correlation. So the fitted models, so for predicting Y from X for all these different panels here, have the same slopes, the same intercepts, the same standard errors. And so the regression model for all these so artificial data sets here is 0.5x plus 3, and the correlation is always 0.82. Right, so it's really everything identical here, but the numbers, of course, are different. So for each of these data sets. So, and if we take a look at the scatter plots for those data sets, so for these XY pairs, or vectors, so XY vectors. So then we see the extent that these data sets are actually different from each other. And so actually only for, so the panel 1, so there seems to be something like a linear relationship between the 2 variables. Whereas for panel 2, we see something that is like a perfect linear relationship for all but one value that is an outlier here, right? So this is basically, that would be, so all the other points lie on a perfect straight line. And so the only, so we have this one outlying value here, which basically destroys this perfect relationship. And then for panel 3, so it's very clear that the relationship between X and Y can actually be better explained by a nonlinear, by a quadratic relationship. I actually might have confused the two, but I think that is panel 3 here and that is panel 2. My apologies, but it doesn't actually matter, it's just for illustration purposes. And then so for panel 4, we see that actually so our predictor is a constant. So we have so it's all the same value, right? So for all cases. And then there's just one outlier that makes it possible to fit a regression model at all, right? Because we have learned, say, if we have a constant predictor, right? So then we cannot fit the regression models the same way that we cannot calculate correlation if we have 0 variance in one variable. So again, right? And those, so all these different data sets here, so basically they're, if you fit them using the simple linear regression model, they're absolutely identical. So the descriptive statistics are absolutely identical. The intercepts, the slopes are identical. The correlation is identical. Everything is the same, but they're fundamentally different. And for all, basically, but this first data set here, a linear relationship is an inappropriate characterization, right, of the data. So that means if we would rely only on our regression model as such and the numbers that we are getting, we would come to completely inappropriate conclusions. So that is why it's so important to look at your data. Okay, so let's talk about the so the different aspects that need to be met for our residuals or error terms in more detail. So I mentioned earlier, so that the relationship between the predictor and the outcome has to be a completely linear one. So that means, and if that is the case, right? So if we have a linear relationship between our predictor and outcome again, right? And real life, nothing is ever perfect, right? So it's never a perfectly linear relationship, but it has to be reasonably close to it. So then the residual plot will be rectangular in shape. Yeah, so that means that the predicted values and the residuals have a horizontal line relationship. Yeah? So that means that the residuals basically are, so they fluctuate around the same mean, right, which is 0, around the, right, so around the 0 line, so they have the same spread, right? So that means that what creates this rectangular envelope. So, and this rectangular scatter plot suggests that after the linear relationship between x and y is removed, right, because we're fitting we're plotting the fitted values, right? So that means we are not plotting x versus y. We're plotting. So on the x-axis we have our y heads. So these are the predicted values, and on the y-axis we are plotting our residuals. So that means, right? So what? So we're taking out the linear the linear part of the relationship between our two variables, right? So that's why there's no slope left. Then so there is no systematic relationship between x and y, right? It's just zero correlation. And so if the relationship between our predictor and outcome is not fully linear, so then the scatter plot of the residual values will be curved or irregular in shape, right? So then we don't have this nice rectangular shape. All right, so that again is an illustration for the sample data. So for these 4 different panels, and we see that only, so for panel 1, so the scatter plot, so again, right, on the x-axis, we have the fitted values. So that is the y values that are predicted. So the predicted y values, right, from the model based on the axis. And on the y-axis, we have our residuals, right? You see that the mean is 0, and they should just randomly, right? So be randomly scattered with the same spread across this 0 line here, this horizontal 0. And that is the case for panel A, where we already determined based on the scatter plots, it's most likely the only case where a linear relationship is appropriate. And as I said, so nothing is perfect in real life. So this line is just basically gives you the mean. So, or approximation of the mean. And that is reasonably close to this horizontal line. But then we see for panel 2, right, that that is actually, after removing the linear part of the relationship between x and y, we see that so the residuals show a curvilinear relationship with the fitted values. So that means there's clearly a quadratic component that needs to be added to the model as an additional predictor, right? So that means we would have to run a multiple regression where we just add to this linear term a quadratic term. We'll talk about that next week. And then here, so that was a model where basically all the data are on a perfect, basically it's a perfect relationship between our predictor and our outcome. There's just this one outlier here that basically destroys this perfect relationship. And this outlier creates an artificial trend or systematic trend in our residuals, such that the residuals decrease as our fitted values or predictor increases. And so, right, that is of course a violation of the assumptions, as that should not be the case. Should always be like a horizontal line, mentioned that. But in this case, it's highly likely that this is just some error or so. And then of course, we never have, in real life, in social sciences and neuroscience, we never have a perfect relationship. So here in the last panel, panel 4, we can see that so the basically the outlier is the one that makes the model estimate, so that makes it possible to estimate the model at all, right? Without the outliers, we would have a constant predictor, and so our basically all have the same fitted value, of course, and they deviate more or less from this predicted value, but without this one value that has a different x, actually, we wouldn't be able to to fit a model at all, right? So because there's no variability in our predictor. All right, and then of course the y, so the outcome variable varies, so that's why the residuals are non-zero, right, with these values. All right. Let's talk about homoscedasticity, right? So this assumption that so for each value of my predictor, the standard deviations of the variability of the residuals of the error terms has to be the same. And that means that we do not expect to see any variability in the or any change in the variability of the residuals across the range of our fitted values. So, and then again, so we see the classic residual plot, right, where the fitted values are on the x-axis, the residuals here on the y-axis. And here it's very clear, right, so that for, so the smaller our fitted values are, so the smaller is the variability of the residuals, and then so as the fitted values increase, the variability of the residuals also increases. So this is a classic example, right? What I mentioned earlier for this for a non-rectangular shape, so this funnel shape, so which indicates that so the data are we have heteroscedasticity here, and this is clearly a problem. So here are more examples. So for violations of so the homoscedasticity assumption. So here the first plot looks good, right? So here we have like roughly, as I said, this, I mean, there's always a little bit of variation, right? So but roughly this rectangular envelope. So we see more or less so the spread of the residuals across, right? This is all around 0 here, and it's roughly the same across a range of fitted values. So whereas here we see an increase, right? So for lower fitted values, it's clearly there's a spread, so the variance of the residuals is smaller than for larger fitted values. And here we see basically on both ends, so for the extremes of our fitted values, so at the end of our range. So the variability, the error variability is much higher than in the center. So these two would be violations, and this is that looks okay. There, so let me actually check whether there's. Why do you disappear? Okay, so that is just a comment, and that's something that R gives you when you ask. So when you basically use the plot function in combination with your fitted model. So it gives you something that's called a scale location plot. The scale location plot is very similar to the residual plot. So the only difference is that it uses the square root of the absolute value of the standardized residuals, right? So rather than the standardized residuals themselves, it uses square root of the absolute values. And so the big advantage of using this alternative display is that you can see headers, so you can identify heteroscedasticity by basically a trend, right? A slope, basically a non-zero slope of your trend in the in this relationship between fitted values and standardized residuals, right? So whereas in the previous slots, if we go back, so you always have to, right? You sort of have to check a little bit, how does it look, right? And do they really, do they spread evenly around this line 0? So here you can tell, well, if this red line is not a horizontal line, then I probably have heteroscedasticity, right? So, and here that looks fairly okay, right? As I said, nothing is ever perfect in real life, so that would be an okay plot, so not like raising red flags, but here we have a relatively clear violation, so that was most likely violated the homoscedasticity assumption. That's the opposite of what's supposed to do, but anyway, information. We can also, R actually has a whole range of formal tests or statistical tests to check heteroscedasticity, although I would always, I mean, they can supplement the, so the visuals, the graphic displays, but they should never be a standalone for the very reasons that we have discussed so many times, right? So that they depend on the sample size and that we never have something like perfect, perfect homoscedasticity, perfect normal distribution. So yeah, so they can supplement your your graphic checks, and ideally they will come to the same conclusions, but I would always rely more on the visual displays. So one is this, so the, actually I'm not sure how to pronounce this, Bruch Hagan tests, I would say Bruch, probably a German name. And it tests whether the variance of the residuals from your regression model is dependent on the values of the predictor variables. So basically, just what we don't want when we test homoscedasticity, right? So it should be independent. So and it's a chi-square test. So it has a test statistic that follows a chi-square distribution with k degrees of freedom. So k is the number of predictors in your regression model. And then as usual, so if you're tested or if your test comes up with a p-value that is smaller than your predefined alpha level, then you can assume heteroscedasticity, whereas if it's like above that alpha level, then you can maintain your null hypothesis. That's a data homoscedastic. Oh. Drives me nuts here, the animations. Okay, so the next aspect, right, or the last aspect, so of the bivariate normality assumption was the independence of errors. And so unfortunately, so that is the most important, so unfortunately, okay, this is the most important assumption, most important one, but it's the hardest to check and often impossible. So we have to make sure, we were talking about that earlier, we have to make sure with good design that our errors are independent. So there are very few ways of checking that post hoc, right? But unfortunately, violations of this independence of errors is one of the most dramatic problems that really violates our, or threatens the validity of our generalizations or conclusions from the model. Okay, so I mean, very often makes intuitively sense. So those, so the error independence is violated in time series models, right? If we model some, so something where, so in this case, so the predictor is time, and then we model some time dependent process, right? And then in most cases we have some dependence over time. It's called autocorrelation, right? So EG data is a good example. So it's not that most likely. So the brain signals that you measure at one sampling point will be similar to the ones that you have just measured 1 millisecond before. So it won't be like completely unrelated, right? It's not like constantly randomly oscillating. So and so such serial correlations, the errors, right, also called an autocorrelation, so between consecutive errors, right, it could be like 1 or like 2, right, it depends on how far that reaches, often indicates a need to improve your model, right? So if you detect something like that in your data, you can also explicitly model that autocorrelation, right? So you can, when you do like fMRI analysis, for example, you often want to model an autocorrelative component in your data. So you want to explicitly include that in your regression model. So I mentioned earlier, so sometimes it can be a byproduct of the violation of the linearity assumption. So if, for example, a simple straight line is fitted to data that are growing exponentially over time, right? So then that can lead to an autocorrelation in your error terms. And so it can also be violated in non-time series models if errors tend to have always the same sign under particular conditions. Yeah, so if you, for example, if your model systematically underpredicts or overpredicts what will happen for a certain value for certain value configurations of your predictors, right? So in multiple regression, we will talk about that. So if you, for example, have like 2 predictors, and then for so let's call them x1 and x2. If, for example, you see a systematic overprediction for low x1 and low x2, but systematic underprediction for high x1 and high x2, so that would be also a violation of this assumption of error independence, and that can happen, right? So often it helps in these cases to include another, so it can indicate that you forgot some important moderator, so a third variable that that moderates the relationship between your predictors and the outcome, and that can help, right? In this case, if you would include a third predictor, that might actually resolve those problems, or you include an interaction term, so that can also resolve your problems, which is basically another predictor. Okay, so that is just an outlook for what we are going to look at next week. All right. So as I said, so we have a chance to determine or to look at graphical displays to check our error independence assumption if we have some natural ordering to our data. Yeah, so for example, if we know, so if we run the study and we know, it's always a good idea to check so a trend over time. So I mean, we usually know in what order so the data were collected, right? So what, for example, if we work with human participants, we know, right? So we can order them by date. So, and then it's always good to check whether we see any systematic effects here over time. Sometimes there's some other natural order in our data. It could be like spatial, like could be distance or so. It always depends on what data you're working with. So, and what you're doing is basically then you're plotting residuals so against this order factor. So it could be time, it could be, as I said, it could be spatial distance, it could be any other order that you're aware of, right? So I'm always using this example of so an exam, and then so you have the students sitting next to each other, right? You have your plan, and then that is also an order that you could use to check whether you have you see correlation between your error terms, right? If one student is copying from the other, for example. And so then once again, we were looking at that when we were talking about screening, right? So here you have error terms that are independent over time. So that means, right, so from knowing so what the value of the residuals is here, right? So you cannot tell what the next residual will be. So there's no systematic relationship. Whereas here you have a very clear positive correlation. So it means, right, if so this residual is larger than 0, right? And the next one will most likely be very similar. Same is true for this one, right? And then here, so they're more, so this, right? It's not that this could suddenly be here, right? So you basically see they will be close to each other in their values, right? So consecutive time points. And that is an example for a negative correlation over time, so that if one is low, so the next one will be high and vice versa. But I mean, I don't know what's going on with these animations. They're driving me really crazy here. Okay. So you can also have a residual plot. So if you try to find some order effects, so for example, if you plot your residuals over time, so like the observation order, so it's the order in which the data were collected, you can also see so like a positive trend here, right? So it looks like a linear function here, so the residuals versus time. And so that means that there's some variation in the outcome due to time, and that could be yeah, so in this case, it might be good to simply include time as an additional predictor in your model. That could help. We'll just remove, right? So we'll move that linear trend. Then you have your desired null relationship again, right? So your random fluctuation around 0. If you just basically use the observation order as an additional predictor, right? That way you pull out this linear relationship. So one point that I wanted to mention, there is something that is called the Durbin-Watson statistics, a formal test for for autocorrelation of your residuals at lag 1, so basically really between consecutive time points. So it does not take into account, right, so some potential autocorrelation between like, so time points that are 2 points apart from each other. And it makes only sense to run the Durbin-Watson statistic if you really have, or if you know what the order of your data is, and if you have to input them in the right order. Otherwise, it will give you nonsensical results, right? So you cannot just run the Durbin-Watson statistic on your unordered data. So that doesn't make sense, right? So it's sometimes not quite clear in statistics textbooks that is the case, right? So it's only appropriate, right, if you have correlations over time or some other kind of natural order. And then you have to put the data in the correct order. So you have to arrange them in the order to run the test. Okay. So then last but not least, we also want the residuals or error terms to be normally distributed, and then our beloved QQ plot comes into play, right? So where we are plotting the theoretical percentiles of the normal distribution on the x-axis and the sample percentiles of the residuals on the y-axis, right? In most cases, R is doing that for us. So we have here the theoretical quantiles, and there we have the empirical quantiles for our standardized residuals. And ideally, so we want them to be on straight lines. I won't go over the QQ plot again, but I mean, you always have to check it. It's part of almost all diagnostics for many tests. So you really have to be comfortable with it. Yeah, and so here. That is just an example that looks pretty good, right? So we have here this one outlier, which would need further inspection. But apart from that, so it looks reasonably okay here. So the assumption, this is a clear violation, right? So especially in the upper tail, for the distribution of the standardized residuals. So these are not normally distributed. Okay, so these were the formal assumptions that have to be met for our t-test and our f-test. To test the regression weights, right, t-test and the r-squared f-test. And so, but a really big problem for regression analysis can be outliers. I mentioned that before. So outliers also violate the assumption that residuals should be not, I mean, you could see them, so it's always like it varies a little bit whether outliers are seen as a violation of the assumptions or not. You could see them or define them as a violation of the assumptions, because one assumption is that the error terms, so residuals, are normally distributed, and outliers certainly contribute to making them non-normal, so these distributions. This is just a reminder, right, so that we differentiate between univariate and multivariate outliers. For regression analysis, the multivariate outliers are typically a bigger concern than the univariate outliers. And then of course for a simple regression model, it's the bivariate outliers that we are concerned about. For simple linear regression, for multiple regression, it's of course multivariate outliers. So more than 2 variables. And in both cases, so if you're, no matter whether they're talking about univariate outliers or multivariate outliers, so an outlier is a value whose probability is unexpectedly small, right? So that is what characterizes an outlier. So value is an unexpectedly small probability. And so that means in the univariate case, right, if you're focusing only on one variable, right, so in this case, when we are talking about simple linear regression, only on the predictor variable or only on the outcome variable, then that means it's a point that is far from the mean, neither direction. And in the multivariate case, it's a point that is far from the centroid, right? So that means it reflects an unusual combination of scores on different variables. So it's very important to keep in mind, right, that the multivariate outlier might be distant from the rest of the data, even without extreme values on the individual variables. So that means, a multivariate outlier does not need to be a univariate outlier. Yeah, so it's possible that a data point is a multivariate outlier and it's a perfectly fine, it's perfectly good looking in terms of the univariate distributions. And that means it is a case with a large residual. Let's say if they're, can have both, but so if we have a case that has like a, yeah, good looking, as it's not far away from the mean of X and not far away from the mean of Y, could still be an outlier if it has a huge residual, right? So that's not predicted very well by our regression model. So these are a few examples here. So for our, a little bit, so where what outliers could look like, right? So both the univariate outliers and the bivariate outliers. Of course, our univariate outliers are easier to spot in terms of a scatter plot or with visual display. So we can, as I said, we can use either scatter plots, we can use box plots, right? So we can use histograms to spot for univariate outliers. And so it could be either an extreme X value, right? So one that is far away from the other X values, could be an extreme Y value. It could be extreme Y and X, or it could be a distant data point, right? So that would be one that has a really large residual here. And to spot univariate outliers, of course, we can also use the z-scores. That is another, it's a numeric measure, right? Or some test statistic, formal test of outliers. So multivariate outliers are spotted using different statistics. So we will talk today a little bit about Cook's distance. Next week, we will talk about more statistics that we can use to spot multivariate outliers. And so Mahalanobis distance is another one. That can be used to determine whether a value is a multivariate outlier or not. But so as I said before, being an outlier as such is not necessarily problematic. A question is whether you're influential for fitting the regression model or not. All right, so after talking so much about influential points, right, influential outliers, so we will finally define them. So yeah, so what is meant by an influential point? So an influential point is one that distorts the regression coefficients. So that means it has more influence than it deserves. So what does it mean it deserves certain influence? So if we have, so normally if we have like n data points in our sample, right? So n cases, n subjects. So then each data point, so each case should have a weight or an influence of a 1/n, right? So that is basically every value should have the same, makes the same contribution to estimating the model. And so for outlying observations that are influential, so they can have a weight of 10, 20, or even 50%. So they have a huge influence on the regression parameters, so how we are fitting the model. And that is an undue, right? It's an undue influence, and that leads to serious distortions in the estimated coefficients. And so in general, as a general rule of thumb, the smaller your sample, so the more problematic are those influential cases. So the more problematic are outliers, right? So if you have a couple of outliers in a huge data set, they probably they don't make a big difference. If you have a smaller sample, you have huge outliers, so then they can be a much bigger problem. So, and so basically one way to determine whether an outlier is influential or not is to just remove that value, that data point from our analysis and rerun the regression. And then to check whether so our regression model actually changes a lot. So when we remove that particular case. So here we see an example on the left side where we have an outlier, right? So here a value that is extreme in terms of both, so the X value and the Y value. However, so this outlier here lies on the regression line. So if we would remove that from the analysis, nothing would change. It would be exactly the same. So this is an outlier, but it's not problematic. It's actually not influential. Here, on the other hand, so on the right-hand side, so we see, so that is basically a little bit of different location. Here's this outlier, and so the black line is the one so that results if the outlier is included in the in estimating the regression model. The green line is the one that results if the outlier. Sorry, 1 second. The green line is wrong. It's odd. The green line, sorry about that. So the green line should be here. So that is too high. It must be something with the formatting of the slides. So I need to correct that. So the green line should be here, right? This should go right through the, basically it's just too high up. So it should go right through the data points here. But the angle of the two, I mean, that is the decisive point here, just a little confusing because does not fit the point, it's actually the data. So that as you can see, the slope here changes dramatically if you exclude this, so this outlying value here. So that is an influential outlier, and that is problematic. And in order to determine whether an outlier is influential or not, so there are two diagnostic statistics that are very relevant. The first one is a distance measure. It's also called discrepancy measure. And the second one is called leverage. So what is leverage? So leverage is the horizontal deviation. Yeah, that's the horizontal deviation, but it does not mean whether, so I will explain in a second. So it's basically a measure of how unusual the x value of a point is relative to the x observations as a whole. Yeah, so it's in simple regression, it's just the squared distance of that point from so the mean from our mean x value. So from the mean of our predictor variable relative to the sum of the squared deviations of all points from x squared. Yeah, x bar. Sorry. So it basically, so what you need to keep in mind is, right, so leverage is a horizontal deviation, and so the more a point deviates as a horizontal deviation, so it's in a horizontal direction, so the more it deviates from the other axis, so the more influence potential it has. Yeah? And leverage always takes values between 1 and 0, and it has an absolute minimum of 1 over n, so where n is a sample size. Right, so and so a 0 leverage would mean the point has no potential to influence, so the regression estimation, and 1 means it has a perfect influence over the regression, the estimation of the regression coefficients. So, but that is not the whole story. So we also have to take into account another measure, and that is the vertical deviation. So that is the deviation on the y dimension, right, of our dimension of our outcome variable. And in order to determine this deviation, so we are looking at something that's called the externally studentized residuals. And so this is a bit also a confusing term, because very often, so they are only called the studentized residuals. So it's not that people don't make a distinction between internally and externally, but they are very different. So it actually would be better to always include that. But anyway, and so sometimes there are also other labels for this kind of residual. And so what is a studentized residual? So it's a measure of the size of a residual for given data point, standardized by the estimated standard deviation of residuals based on all data but the given point. So that means, I mean, a standardized or an internally studentized residual. It's just the usual, right? It's a residual that is scaled by an estimate of its standard error. And the standard error is estimated using the entire data set, including that data point, right, to which the residual belongs. The difference for the externally studentized residual is that this very data point is not included in the estimation of the standard error. So it's basically excluded. And so that, of course, so that helps to identify how influential that particular point is, right? So because if the standard error changes dramatically, or it's much smaller, right? If you don't include this data point in the analysis, so then this is an important. So then this will make the residual much larger, right? So then the standardized residual, right? Because then because it's the denominator, right? So then the entire term will be larger. And so the studentized residual describes how unusual a point is relative to the regression line computed without that point. Yeah. So how unusual is the point relative to the regression line that is computed without that very point? Yeah. And the reason is that so you have to exclude it is because that point could influence the regression line a lot, could basically pull, right? If it's influential, then it pulls the regression line towards it. Right? An influential point pulls the regression line closer to it. That will shrink that makes the residual smaller, so the absolute residual. And that's why it's important to exclude that data point from the analysis, right? And then to use that, so the standard error estimate, so to determine how large the residual actually is. Okay. So, okay, so I'm just reading my notes here. One thing that I wanted to mention is so that, and that's also in R, as the case in R. So as I said, so the internally and externally studentized residuals. So the internally studentized residuals, so where basically the, so this case is included in the estimation of the standard error, standard deviation of the residuals, that is often just called the standardized residual, right? So and then R, it's R standard versus R student for the two, but it's not 100% correct because they're actually the externally, internally. It's a little bit misleading because standardized, you think of like a Z transformation, which is not, it's similar, but it's not exactly what you're doing here. So, and so this is just an illustration. Unfortunately, it's a little bit small, but so to show you what happens if we have values with large leverage versus large discrepancy. So large studentized residuals do not necessarily mean that the data point is influential. So if such outliers are near the mean of X, if they're near the mean of our predictor, they do not affect the slope of the regression line. They just affect the intercept. We don't care about the intercept. We can see that here, right? So this is, so you see, right, this data cloud here, this regression line, this blue line. And here we have a value that is very close to the center of X, but it has basically no, so the leverage is very low, right? So in this case. And the discrepancy is also, I mean, for both cases, the leverage is low, right? But the discrepancy here, so the studentized, the residual is very, very small for this point. And you can see that here, so the X is 0 and the Y is 0. So that's really in the center of your data cloud. So if we now change things a little bit, it makes the, so the Y value really, really large. So we make that residual huge here, right? So we creating a ginormous residual. Then we see what happens. It's a little bit, as I said, it's a little bit hard to tell as we're pulling the regression line a little bit up, right? So it's a little bit higher. So the intercept is getting a little bit more positive. But the slope of the regression line does not change at all. Yeah? So it means if a value has a large residual, it is not influential as long as it's close to the mean of your predictor. So the same way, a large leverage, yeah. So basically a large X as an X value that is very far away from the other X values doesn't necessarily mean that the point is influential. So if such outliers are near the regression line, yeah, as in this case here, right? So we have a value that is very unusual with respect to the other x values. It's a huge outlier here, right? So it's distant from the data cloud here, from this envelope. But it lies almost perfectly on the regression line, so it has absolutely no influence, right? It does not change the regression parameter. Well, this is not an influential case. However, if we have, right, so that is there's an extreme x, but the so we don't have a large residual here, right? So that the y value is in the center of our distribution here. However, if we have a case that has both a large leverage and a large discrepancy, right? So it's basically, it has a large deviation in both, so on the y dimension and the x dimension. So then we can see how that point pulls, so massively pulls the regression line. And you can see that, right? So how that single point, just not a tiny sample, right? You can see how this one single point here pulls the regression line in its direction. That is an influential point. That's a problem. This point has an undue influence on the estimation of the regression parameter. So, and that means, right, influential points are those that have high leverage and high discrepancy. Okay, so if we want to actually obtain discrepancy, if we want to estimate that or determine what is problematic in our data sample, so then we can identify cases that have large studentized residuals. Yeah, so that means, say, if the residual is larger than the t-value for alpha over 2n, so n again is a sample size, and that could be indicative of an influential outlier and are worth checking for validity, right? So these are just cases that we are, so here for this example, right? So we have, so this value here that has a large residual, a large studentized residual, and here I'm talking about an externally studentized residual. That means, so if we would remove that data point from the regression function, so then that would dramatically change the model. Yeah, we can see that here, right? So the corresponding value is really high, and so we want to check that. So in this particular case, because this outlier here is in the center of the x distribution, it doesn't actually have much of an influence on the actual slope parameter. Right? In this case, it just pulls the regression line. It just changes the intercept, right? It pulls the regression line upward. It has a potential, right? Always have to keep that in mind. It has potential to be influential. It has a potential to influence the estimation of the regression coefficients and also the estimation of the slope, but only if it has not only high discrepancy, not only a large studentized residual, but also if it's if it has high leverage. Yeah. So the leverage was low here. So if we want to find a criterion for for spotting values that are problematic in terms of their leverage, then I thought I had, wait a second, I'm a little bit confused because, no, never mind. I thought I had another slide. So if we wanted to check whether a point has unusual leverage, so whether it's potentially problematic because of its leverage score, so then we have to compare it to some threshold, right? And there are different guidelines in the literature what the thresholds are. And so most of them are based on the mean leverage score. So the mean leverage is so k plus 1 over n. So n is the number of cases, k is the number of predictors. And so the rule is that the leverage for a given data point should be no more than 2 or 3 times the mean. Yeah, so that shouldn't be more than 3 times k plus 1 over n. So here for this example, so right, so for these for all data points in this example here, and these are the corresponding leverage values. So the mean is 0.66. Sorry, 3 times the mean is 0.66. So that is one that deserves like closer inspection. Yeah, and we already know that is one that is potentially influential. So that because it's right, it does not only have a leverage, it also has a relatively large discrepancy, a large residual. So if we want to measure how influential a case is, then we have to take into account both, so the leverage and the discrepancy of a point, right? So we basically define in a quantitative way. So we define the influence of a point as the amount by which the slope of the regression line changes when the point is removed from the data set, and then we compute the new slope. The difference between the slope without and with that point, so that is a quantification of our influence, right? So that's another example here, right? So with the outlier and without the outlier, we see the corresponding regression equations. We see that the slope parameter here is minus 1.6 in one case and minus 2.5 in the other case. So that is a huge difference. And in order to spot influential cases, so there are different measures have been suggested. So one is that's very frequently used and very prominent is Cook's distance. And Cook's distance measures the normalized change in all regression coefficients combined due to the deletion of an observation. So that means, so of course, for our, because we are only talking about simple regression, we have only one predictor. So we have basically only one regression coefficient. If we forget about the intercept, which is not important. So it doesn't make much sense, but Cook's distance can also be used for multiple regression where we have like multiple predictors and also multiple regression coefficients. So it takes into account the effect that so deleting one case has on all regression coefficients and how much the regression line changes without the data point. So in cases with Cook's distance greater than 4 times the mean, so mean across all cases, right? So we are can calculate Cook's distance for each individual case in our data set. So may be classified as influential. Yeah, so that is rule. So what is even better than just relying on Cook's distance is simultaneous plot of Cook's distance and the studentized residuals for all the data. And so that may suggest that some observations need special attention. It's easy to do that in R, to plot that in R. Okay, so since it's already relatively late, I'll think about, and maybe we actually wrap up, so we complete the multiple outlier topic, and maybe we can also talk about estimation, and I will do robust regression next week. Okay. So everything that we have talked about so far when it comes to outliers, so it was limited to one single outlier, right? So that means so also the validity of these tests is basically limited to cases where we have one or very, very few outliers. And so the problems that we have with outlier identification are aggravated. So when we have more than one outlier, and so more outliers we have in our data set, so the more complicated it gets. And this problem is even worse when we have more than one predictor, so for multiple regression. So in what I would like to show you are two effects that are known as masking and swamping, and that come, so these effects so come with if we have more than one outlier in our data set. Mm-hmm. So if we basically, if you have only one outlier, then your regression diagnostics, so the numerical methods and also your plots will reliably identify this outlier. If you have multiple outliers, we're getting into trouble. We're facing problems because it's hard to disentangle the effects of the individual outliers. So I will show you in a second. Okay, So the first problematic effect that can occur when we have multiple outliers is called masking. And masking is when a group of outliers serves to move the fitted regression line near enough to them that they no longer appear to be outliers. So here in these graphs, we have, so see this red case here, that red point is one outlier. So the red regression line is always calculated without the, the blue regression line is calculated without the outlier, and the red regression line is calculated with the outlier. I'm not sure why I'm mixing up everything in my slides today, so have to check that as well. And here you see the basically the outlier statistics. So for the influence of this red point here, so the leverage is 0.434, the studentized residual is 3.894, so quite high, right? It's, I mean, you see that the deviation from the regression line is quite massive, and Cook's distance is also quite high here, right? So, and now, so in the right figure here, see what happens if we have a few more outliers. So now the outlier is masked. So why is it masked? So now if we basically calculate the regression without that outlier, without that single red outlier here, then it's almost the same as if we would calculate the regression model with the outlier, right? So you see, so when it was a single outlier, it was a massive difference. Now that we have multiple outliers here, so excluding one of these outliers actually doesn't make a huge difference. So that means all these methods like Cook's distance, et cetera, that rely on removing one case from the data set are basically not very effective if you have multiple outliers in the same region. So that is a problem. It's called masking, right? So, and then again, I apologize. So the blue regression line is calculated. No, it was right. Demented today. So the blue regression line is calculated without the outlier. That is basically the data is a fit for the black circles. And then yes, the red dotted line or the red dashed line is calculated with the outlier. So with this red outlier, and you see how the outlier here pulls the regression line towards it. And then if we have more outliers in the same region here, so and we exclude only the red one, then that actually doesn't make a big difference, right? And that means that all the measures that we use, so for measuring influence of Cook's distance and leverage and the studentized residuals, so see how the value changes here for the studentized residuals. So it's basically, it's no longer problematic. So leverage is smaller and Cook's distance is negligible here. So, and that is a huge problem. That's called masking, right? So another problem that can occur due to masking is called swamping. And swamping is when a group of true outliers mask each other and simultaneously make a point that is not a true outlier appear to be an outlier. So it's even worse, right? It's not only that, so we have, so swamping occurs always in combination with masking, right? So we have, so here again, we have only one outlier. And then this is a data point that we are focusing on, right? So here's the SR, is the studentized residual for the data point. So it's all okay, right? I mean, if there's only one outlier in the data set, then again, right? So the blue line is without the red outlier, the red line here is with the red outlier. However, if we add all other outliers here, pang, suddenly our data point that is not a true outlier becomes an outlier. Right, so we see the studentized residual is really large for this data point here now. So that is swamping, right? So if true outliers make a non-outlying point appear to be an outlier because it pulls a regression line towards them and away from the value that is not an outlier. Okay. So if we have multiple outliers, so what are we going to do? So that's a problem, right? So because all the well-known statistics for evaluating outliers are based on a single mean displaced outlier model. So they're basically assuming that only one point is an outlier. And Yeah, so that basically or a group of n observations that or a sample has been contaminated, has been invaded only by one single outlier observation. That is problematic. And so there are two fundamental approaches to detect multiple outliers. The first one is called a direct approach that uses sequential algorithms to isolate the outliers. And the second one is called an indirect approach, and that plots a mean function using a robust regression method. And this robust regression method is a method that either removes outliers from the data set or estimates a model, or it diminishes basically it downweights the outliers so that they have less of an influence on the estimation of the model. Okay. So maybe I want to give you like a little bit time today, but let me maybe wrap up the multiple outlier direct approach because it's relatively quick. So so we basically have two fundamental mechanisms that we can use when so we want to utilize a direct approach to multiple outlier detection. So they're both based on sequential deletion. So no, on sequential mechanisms. So the first one is sequential deletions. It's also called the backward search. And the other one is called sequential additions, a forward search. So sequential deletion basically starts with a full data set, and then it sequentially, so stepwise, removes values that are identified as outliers. And the sequential additions, also forward search, actually does the opposite thing. It starts with a clean data set, with a subset of the original sample, and basically starts with a set that is assumed to be a clean data set, so a clean sample without outliers, and then it sequentially adds more observations, so more clean observations to the subset, and then it stops at some point when it identifies some, so the next value that it tries to add to the subset as an outlier. So again, so the backward search, so it starts with the entire set of observations, and then it removes outliers one by one, and it uses like certain criteria, that's like the largest absolute value, or of the residuals, or a transformed residual. And the forward search does the opposite thing. Yeah, so it starts with a small subset of the data that is selected as the initial clean basis. And then the model is fitted on based on these clean observations. And then more data points are added to the model. And as this basically subset grows, right, as we make our sample larger and larger, then we constantly check the parameter estimates, the test statistics, and measures of fit. So until we reach some threshold. And at this threshold, we decide, okay, so this next value is an outlier, so we're not including that in the model anymore. And so the forward search methods are usually much better than the backward search methods. Okay, so maybe I'm going to stop here today because the indirect approach includes robust regression. I just wanted to mention one more thing because it is important for the assignment, sort of. Maybe not, but not really. Actually, not really. Maybe I'm just confusing you more with that than it helps. Yeah, I think it's fine. Let's talk about that next week, and let's call it quits for today. So I don't think you'll need that for your assignment, for next assignment. Alrighty. So then I would say you can just use maybe like 10 or 15 minutes if you want to discuss your next assignment. And then if you have questions about the assignment in particular, So you can ask me afterwards. We can also go just run in R. So some of the social commands from the tutorial for this example data set, so that you have seen them and that I can quickly show you what how it looks like and then what the diagnostic plots look like. So to make it so that at least we have I've commented on that. All right. Okay, so let me just create where I think I have to create the breakout rooms. So manually. Well, I'll let you choose a room. I'm creating 4 breakout rooms, and then maybe you guys can, so based on your group number, so I make rooms 1, 2, 3, 4, and you can join the rooms based on the numbers, and I don't have to put your names in it because otherwise it will take me probably 10 minutes to do that. Yeah. Okay.
So we're in breakout rooms for the next 15 minutes?
Yeah, and then, so that is just basically give you a chance to talk as a group about the, so the next assignment, and then afterwards I will be around to either answer questions that you have, and also I wanted, just very quickly, I wanted to show you in our, for the example from the tutorial, what the regression diagnostics look like, and so that we have done it together one time. Do you see the rooms?
Yes.
Yeah, I see them.
Okay, super. Yeah. Hi, Ellen. Actually, we have just started the.
Yeah.
So you can just go to room 2.
Okay.
Maybe.
I don't think I can.
You cannot. Let me. Maybe I can move you. Second.
Oh, I see it now. Okay.
Oh, you see. Okay, super. Hey, Anjali.
I was in the bathroom and then I come back and it was just me and you. And I was like, oh.
Okay. So, alrighty. I would say let me perhaps just share my R screen with you, so my R window, and then I will go very quickly over so the example and then some basics, so just that you have seen it, and then we can maybe talk about questions that you might have. I just think it's perhaps I answer two questions already. Okay, so then let me. So, all right. So I hope you have all the have you all loaded the data set already? So that's the album 1, album sales 1 data set. Okay, super. So, and it's very straightforward, right? So it's similar to the example that we had in class. So, but I think this time it's supposed to be the advertisement. So here you see it's like these two variables, so advertisement, which is I think the money that they spent on advertising here in thousands pounds, and then the number of sales after that advertisement campaign, again in thousands of albums, and it's 200 something. No, it's actually 200. 200 entries, so 200 data points. And so this is the predictor and that is the outcome variable. So very straightforward. No missing values, so it's all good. So it's easy to handle. Okay. And then, so if you want to fit the model, so basically all you need to do is you just have to type the command, right? So, I mean, you can call it whatever you want. So, let me change that here. Oops. Go to the side. All right. No. anyway, okay. So basically, so all you need to do is, let me close that here so you see a little bit more, is to define an object, right? So that is basically a regression object. We will take a closer look at that. You can give that any arbitrary name, so you don't have to give it the same name that I have here. And then you you just assign that the output of the LM function, right? So LM, and then here in the parentheses for the function, you specify the arguments. But first, the first one is a specification of the regression model, right? And as we had discussed yesterday very briefly, so on the left-hand side, there's always your outcome. And then on the right-hand side, that is actually your model. So that's the predictors. And in this case, it's very simple because it's just simple regression. So we have on predictor. So it just sales tilde AdWords, right? So just the name of the variables in the data set. Also, you don't have to use any like dollar operator so to access the columns, right? So the R knows, so LM knows automatically when you give it the data set, right? So what's so it basically knows these are the column names of your data frame. So then you have to specify what the data is, right? So that's the second argument here. You just say data is an album simple. So that is what I called, so you see when I here read in, or when I loaded the, I imported, I'm not good at finding verbs today. So when I imported, so the data set, I gave it the name album.simple. So that is my variable here, right? So it's just the data frame album.simple. So that's how I read in. So this is a dat file. Right, and then I tell him, okay, that is my data frame. That's where you can find the data. And then I just include that here, but I wouldn't even have to do that because there are no NA, so we have no missing data, right? And then if you hit enter, then let me just go my environment, and you can see that, so we basically, it's the data frame here. And here we have a list with 12 elements. So that's the album.sales.simple in my case. And it has the, the elements, fields, coefficients, residuals, effects, rank, fitted values, assign, QR, okay, DF residual, X levels, call terms. Yeah, so you can model, et cetera, et cetera. And if you wanted to do, I mean, we can just try different things, right? So it's always good to experiment with us. So what happens, for example, if we just, calls the object? Now then it gives us a little bit a glimpse of what's in the object. It basically just tells us what the model equation is, what our initial function call was for the LM model, right? So how we created the model. And it tells us what the coefficients are. It's basically the most important information. So, right, that's how you created the model, and that these are the coefficients. So obviously we want to be a little bit more. And if you can directly access the the different fields in your, or the elements of your list, right? If I would go to album simple and then I would just use the dollar operator, then here you can see, right, it gives you the coefficients, the residuals, the effects, the ranks, the fitted values, the sign, even if it doesn't all make sense to you right now, right? So here, if you do that, it gives you basically this information, but it's spit out earlier. You could do also something different, right? You can just look at, I mean, I always encourage you to try all sorts of things, right? So look at the data. This is also 200 residuals, right? And then you can also, I mean, ideally you would do something like, right, if you experiment yourself, you say, test, right? I'm just trying something here. So that's album.sales simple. And now I want to look what are the residuals actually, right? So that's a little bit better. And then I look, what is my test here? Ah, okay. So now I have a, right, it's a numeric vector, and these are the values, right? So, and then there are, oh, nonsense. So there are more elements, right, that you can look into. So what effects? Oh, interesting. So no idea what that is, but these are the effects. So maybe I read in my R help what that is, right? Fitting linear models. What are my arguments and what is my output? So, right, value. Aha, it returns the coefficients. It's a named vector of the coefficients, the residuals, you know, the response minus fitted values. The fitted values, the ranks, the weights, the, okay, offset, model. It doesn't say, why not? Ah, here. Okay. Effects from the fitted model, right? So I'm just basically demonstrating what you would do if you don't know what your model is doing, right? So then you see the effects from the fitted model. I'm, by the way, have never used that before. I don't know either. So effects object. So fine. R is an R object. So fitted from LM. For a linear model fitted by AM, that's what we did. AOV. That's the same thing, just for an ANOVA. The effects are the uncorrelated single degree of freedom values obtained by projecting the data onto okay. So these are your predicted values. Super. Okay. Okay. So that just gives you an idea of what the so what you have in your model, right? So in order to make, you can access it all, right? So directly if you want to. But if you want to like a little bit nice summary of your model, then you use the function summary lm, yeah, summary.lm. It's also for the generalized linear model, but we don't want that. We want that for the linear model. And then you just give it the object that we fitted, right? So album sales simple. And then you get a little bit nicer output, right? So, and it gives you, so again, the function call, so the formula that you use, then it shows you residuals, right? So this is a distribution, so it's other, your, so the range, right? So the minimum, maximum of your residuals, the first quartile, the third quartile, the median. And so we want that to be relatively symmetric, right? So the median around 0, that looks pretty good. Here's the first quartile, and the third quartile should be relatively symmetric. They are here, so that's all good. Minimum, maximum also don't look like crazy. So that all looks like pretty good to me. And then, so this is a heart of the output here. This is our model, right? So that is the most important or the most informative part of the output. So here you have, because it's a simple regression model, we have only two regression coefficients, right? We have the intercept and we have the slope parameter for our predictor. So the intercept, we don't care about that much, but in this case, it's 130. So it's 131. I'm giving up for today. It's 134.1. Yeah, and then keep in mind that it's in thousands. So the scale, you have the corresponding standard error, the t-value, that's just your estimate divided by the standard error, and then you have your corresponding p-value, right? And this basically just means it's smaller than what R can display, but it's basically 0 here. So it's smaller than the smallest number than R can show. And so here but I mentioned that earlier, right? So intercept, we don't care about that anyway. And then, so that's the interesting part here, that's your regression coefficient, so the slope parameter for advertisements of your predictor. And we see that's roughly 0.1, right? So minus 0.1. So if you're not familiar with this notation, it's basically it just tells you move it's a power of 10 basically, and it just means move your decimal point by that number of positions, right? So here it's 2. It basically means 1.341 times 10 to the power of 2, right? So and that means so divided by, right? So 10 to the power of 2. So it means move your decimal place to the left, 2 positions to the left, so that's 0.009612, so roughly minus 0.01. So is it negative? No, it's positive. Sorry, it's I don't want I don't want to confuse you today. I'm terrible. I'm really terrible today. My brain is just mush. So that is not much. It is. I don't know why I think it's a negative coefficient. So this minus here just means that you move your decimal point to the left.
I feel like it's because the plus and minus and all that jazz. Like what?
It would be, if it would be a negative estimate, so you would have the negative sign here.
Okay.
So this
So
just
what
means,
is that then? The plus 0.2 and the minus 0.2. What does that mean?
so that means, so here it basically just means you multiply with 10 to the power of 2, so it's 100.
Oh, okay,
And here
okay.
you mean you divide by 100. So that's a negative sign here, right? So just
Okay,
so here it means move the decimal point 2 places to the left, and here it means move the decimal point 2 places to the right.
gotcha.
If it would be minus, if it would be plus minus 0, 0, then you wouldn't do anything. And if it's like 3, right, then it's 1,000. If it's 4, it's 10,000, etc., etc.
Gotcha. Okay.
Alrighty. So this is standard error for our advertisement estimate, right? So which is pretty small. You see the corresponding t-value is pretty large, and it's also like really small p-value. So that means well, this model explains. So this coefficient is probably significantly different from 0. And here, so these are just the significance codes. You see the little stars here behind, so each regression estimate, and the 3 stars basically mean it's 0. So it's smaller than 0.001. It's not really 0, but it's smaller than 0.001, right? So, so here we can see both are smaller than 0.001. So it's really, it's unlikely that they come. It would be a very unusual finding if the true regression coefficient would be 0. Okay, so the next thing that you see is the residual standard error. Right? So that is basically just the square root of your mean residual, so of your mean residual squares, so or mean sum of squares, so mean sum of squares for the residuals. That's basically how much so your y values, so your outcome values vary around the true regression line. So an estimate of that, right? So that's basically an estimate of your conditional distribution, of the standard deviation of your conditional distribution. So right, so y given x. And so with 198 degrees of freedom, right? So it's always, we are losing 1 degree of freedom, roughly speaking, for each parameter in our model. So we have 2, right? We're estimating 2 coefficients. Then we have our multiple R squared. So that is the proportion of variance in sales, in the sales variable and the outcome variable that can be explained by so the predictor by our advertisement, so it's roughly 33%, right? And so we were talking about the adjusted R squared, right? So R squared, the estimator is positively biased, so it always overestimates so the true explained variance in the population, therefore it has to be adjusted. In this case, it's not much of a difference, so that's good. And then we have here our F statistic, so our F value from this fraction, right? So the model mean, basically mean sum of squares divided by the error mean sum of squares and the corresponding degrees of freedom, right? So it's for the numerator here, and that is for the denominator degrees of freedom and the corresponding p-value, right? So which is not surprisingly also the same as here. So, and that is it's the heart of your regression models and the most important information. So do you have any questions about that, or is it relatively clear what you're looking at here? Despite my confusing. Okay, super. Then, okay, what did I want to do next? All right. So, all right. I mentioned that, right? If you want to do, for example, here. So if you want your standardized residuals, and these are the internally studentized residuals, I know it's super confusing also to me. So that means these are basically your studentized residuals with the data data points, so with the case included in the calculation of the standard error, right? So that's the case for which you're calculating this residual. And that is the function R standard. So that's your internally, right, studentized residual, so the one that includes the given case in the estimate of the standard error, right? And then you, of course, it's for basically you get, if you do that, you get one value for each data point. So for each of your 200 data points, right? So you can see the standardized residual for the first one is 2.9. That's pretty high. Right. And yeah, so they're fluctuating around 0. Yeah. So, and if you want the externally studentized residual, you have to do that. You have to use RStudent. Okay, and then this was a modern album. Right, and again, that is not very meaningful when I show you that, but so just if you compare, right, so the values are not identical, right, so they're different here. So that means, yeah, if we actually exclude, so that for the first data point, for example, if we exclude that data point from the regression analysis, and the residual, it becomes more unusual, right? So the residual becomes a little bit larger. Whether that is, it's not much, right? Just numerically, right? And for the second, do you see any significant deviations here? The 200s? No, it all looks pretty good. Alrighty, so so that just as a side note. And then if you want to calculate Cook's distance, right? Then you're using so the function Cooks.distance, right? Again, you give it your model, and then it spits out Cook's distance for each of your cases, right? For each album. And so again, as a reminder, Cook's distance was a measure of how influential so the data point is. So it basically takes into account both the leverage, so how unusual it is in terms of so the X value, and so the discrepancy or the size of the residual. So that means how unusual it is in terms of its Y value, and only if both are large, so the case will be influential. Right, so, and for Cook's distance, you had the criterion that basically you calculate the mean across all distances, and then if in a given case has a distance that is more than 4 times the mean, then it's probably worth inspecting it a little bit more closely. Okay, all right. So what did I do here? Oh, it's just some nonsense. So no, I didn't want to put it. I want to source to console. Right, so here that is just a graphical display. You see all the distances, right? And you see a few values that have higher distances than the others, so most of them are pretty well behaved here. And that doesn't look super concerning to me. So they all look pretty good from, I mean, you can't really tell, but just by eyeballing it. Okay, so what is really important is, and so that's what I mentioned earlier, is to this plot function that has super helpful regression diagnostics. And so it will, if you have RStudio, it will always ask you to hit return to see the next plot, because it's plotting 4 different ones. And the first is a residuals versus fitted plot. So that is your residuals plot. So it's basically the typical residuals plot. And right, again, so as a reminder, on the x-axis, these are the fitted values. So these are your predicted y's. So it's a mean, actually, mean predicted y. So your y hat based on the x value. So that means, right, if you're, so that would be a predicted y of 150,000, right, 200,000, 250,000. And then you see the corresponding residuals here, right? And what you want is you basically R is nice and gives you like this dotted line here around 0, because that's what they should spread around, right? So they should, so the mean of the residuals should always be 0, and then they should should evenly spread around this horizontal line. And what we can see here is a little bit concerning, because we can clearly see that for lower fitted values, the spread is larger, and then as they get, as we basically go towards larger values, you see that there's a little bit less of a spread. On the other hand, you also see that there's basically have a concentration of the data in this area here. And then there are very few data actually here, which of course explains why we don't see as much of a variation around the this horizontal line. So that, again, I wouldn't be super alarmed by this plot, right? So that is probably more, it probably indicates rather that you have a few perhaps extreme cases here at the end of the spectrum. And that's, so I'm not sure, I mean, we would have to look at the data, what they look like, the original data, but that is not super concerning. All right. So the next plot is a normal QQ plot, and then again, as a reminder, it plots the it is again for the residuals, right? Always for the residuals, and it plots the theoretical quantiles, so what we would expect in terms of the quantiles if the residuals were normally distributed against the empirical standardized residuals, and so that also looks pretty good, right? So that so here, no concerns at all. A tiny bit deviation here at the lower, at the upper, in the upper tail here, but absolutely nothing that would give me like a sleepless night here. So that looks pretty good to me. Yeah, and then you can always, it's always good to also have some, to quantify that a little bit and have a numerical method as well that actually tells you how much of a deviation you see and whether that is within the expected range or not. Okay, so this all scale location plot, again, is very similar to the residual plot. Just a difference is that you calculate the square root of the standardized, of the absolute value of the standardized residual. And then the advantage is that basically you can see heteroscedasticity as a non-horizontal slope here. And that is also, you can see this is not very alarming, right? So that confirms more or less that the previous plot was nothing to be worried about. So it's just that we have like a little bit sparser data here for the higher predicted, for the higher fitted values, but it's not an indication of heteroscedasticity. So that's okay. And then last plot is the residuals versus leverage plot. And so here you can see, I'm pretty sure sorry for forgetting, but I'm pretty sure I was missing a slide in my presentation today. It's weird because I had that definitely in there and explains the plot, but anyway. So so this, sometimes it's not possible to see that. So here you can see there is this red dashed line. It says Cook's distance, a little bit crowded here. And it's actually just in the upper right corner here of the plot. You can see, so basically the critical value, and what you want to look at is always, it can be either in the upper right or in the lower right, which in this case is not evident here. So, and then any values that are above that line would be considered problematic, but here we have nothing to be concerned about. So that is fine, looks just fine. Right, so as I said, so the Cook's distance can be problematic, either the upper right corner or the lower right corner here. So what's above or below, here it's not even so it doesn't even show anything. And here you can see it's barely in the display that it all looks good and really well behaved. So that's also not the reason to worry, right? And that's what I mentioned earlier. So you have you have the residuals versus the leverage. So you have basically both pieces of information that are important to determine whether a value is influential or not in one graph, right? And as I said, so it's the product of leverage and the discrepancy. So that means both has to be large, right, to make a case problematic, to make it influential. So either it has to hover here, right, or it has to hover here, depending on whether it deviates in the negative or positive direction. So these are basically the most important parts, and I think the rest of the assignment is actually more conceptual in nature. But yeah, maybe if you have questions, then you can just let me know, or whether anything was unclear, the wording confusing or so. No?
If like any other follow-up questions, we could email you or put it up on the discussion board, right? Yeah.
Right. So,
Okay.
but yeah, so what would be, I think, most important to me is if you have, because I noticed that frequently that either, as I said, so sometimes I just have a typo or my question doesn't make sense. So it's important to point that out early, right? So, or sometimes it's not quite clear, so it's a little bit ambiguous or not 100% sure what it means. And specifically, I was curious whether there might be any issues with assignment 6.
Actually, I do have a question. I'm sorry.
Mhm.
Really don't want to hold up this class though, because
Oh,
we're all tired. But there was one question where you say I think it was A. Yeah. Regression model, is the regression model significantly different from the null model? What do you mean by null model, by the way?
oh, no, that's a good question. So the null model is basically an intercept model only. So
The what?
when I say the null model, so then it's a model with no predictors.
Oh,
0 predictors. So that is basically a model that predicts, so the intercept model means so that you're predicting the mean of the outcome variable for each value of your predictor. But that's the null model. So it's the model of no relationship, right? So with 0 predictors.
okay, gotcha.
And the intercept in this case would be the mean of your outcome variable, right? Then you have your horizontal line to the mean.
Okay.
It basically means, you could also say, is the regression model significant? I just don't like. It's not actually what we are testing, so that's why I like to put it in a more, but I think more appropriate, because that's what we are testing. We're testing whether it's significantly different from a null model.
Okay, cool.
Does it make sense, right? Basically, I'm asking you, is R
It's
squared
kind of like
different from
a coding version of alternative hypothesis and null hypothesis. So I see what you mean. I'm just trying to figure out how to thus create a null model. But if it's without predictors, then it's probably just minus a portion of a code. So it's fine.
You don't need to do anything here. So it's basically what the question is asking is R squared, does this sample come from a population where the true R squared is different from 0? Most likely, yes or no. So it's basically just running the regression and telling me. I just hated to say, is that significant? Because you always have to think about I want you to think about what you're actually testing and what it means, not only to look at some stupid p-value. then just okay, it looks like it's lower than 0.5, and I have no 0.05. I have no idea what it means, but it's significant. Perfect, right? So, and for regression analysis, so what we are testing is that the question is that model better than no model, right? Is it model better than so predicting the mean of the outcome variable only?
Okay.
And that means, does the sample come from a population where there is a relationship between predictor and outcome that's not zero? Yeah, because in your sample, you will always have some. I mean, it will never be zero. Oh, well, practice never be really zero. Yeah, so and when I'm asking for the regression equation, so then I want you to give me the estimated model. Yeah, so I want you to write down the equation for basically for your estimated model. I don't want you to write something like a B0 plus B1 times X or so. I want the estimated model. Yeah, so not any generic model. Okay. I think everything else is pretty clear, I hope. Yeah, and when I say unstandardized residual values, I really mean the raw residual. It's a raw residual. So not the studentized. Anything else that could be misleading? I'm just going over context. Yeah. Intercept. Okay, now I think that's all right. All right. So effect size. Yeah, we haven't. Oh, that is important. So effect size is not hard, but I knew there was something. So you can go to the end of today's presentation, and there are slides on power and effect. So basically, power estimation or determining sample size for regression and correlation, and there you find the information. So it's basically related to the F statistic. So the effect size for regression is so R squared over 1 minus R squared. It's basically the explained variance over the non-explained. So the ratio of explained and unexplained variance. That's called the F. So lowercase f squared effect size statistic. It's not hard, but so that information is on the slide in the slides. I knew there was something. Okay. All right, so here I'm asking for the studentized residuals, and I mean the externally studentized, yeah? So here, I want the R student. All right, I think everything is pretty clear otherwise, hopefully. Yeah?
Which one did you just say? Our student, our residuals for what?
It's the R student. So I want you to, firstly, it's basically I want you to find the externally standardized, studentized residuals, so the ones that exclude the case when estimating the standard error for the residual, right, for that X value.
No, I mean, like, is this for J, or I'm like trying to like going back and forth. I'm sorry. Is this for J or for I or for K? Where am I looking at? Where is it? I'm sorry.
J. Yes, for J.
J. Okay. All right. Because I'm adding these notes, clarifying these questions. Okay. All right. Cool.
And feel free if you're confused by the, for example, the studentized residuals and what they mean. So this external, this external, it's important. So I know we didn't have much time to talk about it. If you have questions about that and it's conceptually unclear, so please post, right? And then I can maybe add like a better or more in-depth explanation or something that clarifies hopefully a little bit. Okay. All righty, super. Then, yeah, let me know if there are any issues with the assignment. I will post the next one, so assignment 7 later tonight. And I will also work, I mentioned that I will work on a markdown file for R, so that is like a little bit better organized in the Word document that you have right now. Easier to find the relevant code. Okay,
Thank you.
Thank you.
good night.
Night.